Hi everybody, today we discuss about logical equivalences and implications from the discrete mathematics. Logical equivalences. First, logically implications. A statement formula A is said to be logically imply a statement formula B if the statement formula A tends to B is a tautology. That is, A tends to B is tautology, we can say that A implies B or implications B. Then logically equivalent. A statement formula A is to be logically equivalent to a statement formula B if the statement formula A if and only if a tautology. Suppose we prove A if and only if B means we can say that both statement formulas are equal or equivalents. So, then symbolically we write A if and only if B or A equivalents B. Some fundamental logical equivalences formula given here. Idempotence P or P equivalents P, P and P equivalents P, then associative, commutative, distributive, law of the excluded middle, law of double negations, law of simplifications, then dominations, identity, De Morgan's laws, distributivity, law of contradiction, law of addition. So these are all fundamental logical equivalences formulas. Next, inference theory. Inference theory, let A and B two statements, then B may be inferred from A denoted by A implies B. If A tends to B is a tautology. A implies me. We can say that A implies me if A tends to B is a tautology. The simple implies is the inference meta operator. The meta statement A implies B is called a rules of inference. Next, inference theory. So here given some implications formulas, logical equivalences and rules of inference for implication and biconditional. Implication, this one is equivalence. P tends to Q, equivalence, negation P, negation of P and not Q, equivalence, negation P or Q. From the biconditional, first one is equivalence. P if and only if Q, equivalence, P tends to Q and Q tends to P. Then P if and only if Q implies P tends to Q, P if and only if implies Q tends to P. The negation of and implication, negation of P tends to Q, equivalence P and not Q. So these are all some equivalence and implications formulas. Next, logical equivalences and rules of inference related to theorems. These are also implication and equivalence using some theorems with the name modus ponens. First one, then contrapositive, then laws of disjunction, law of hypothetical syllogism, proof by contradiction, proof by cases. So these are all implications and equivalences formulas. Next, discuss about quantifiers. So what is quantifiers? So quantifier means that is a domain of the variables. Let x be a variable and d be a set. P of x is a sentence. Then P of x is called a predicate or proportional function with respect to the set D. If for each value of x in D, P of x is a statement, that is P of x is true or false. That is quantifier means the nature of the variable. The exact mathematical meaning is the nature of the variable. So that variable belongs to some domain set D. And last one, Moreover, D is called the domain or inverse of discourse, and X is called the p-variable. X is called the p-variable. Next, quantifiers. There are two quantifiers, universal quantifier and existential quantifier. First, see about universal quantifiers. Let P of X be a predicate and let D be a domain of the discourse. The universal quantification of the P of X is the statement like that: for all X, comma P of X, or for every X P of X. The symbol for all is read as for all and every. And for all X P of X, or for all X belongs to D P of X. These are one place predicate because we are using only one variable for the statement X. Then last point, two place predicate. Two place predicate means we use the statement two variables, that is X comma Y. For all X, for all Y, the statement P of X comma Y. So this is two place predicate. Then existential quantifier. So here the same, P of X be a predicate and let D be a universe of discourse. The existential quantification of P of X is the statement there exists X, comma P of X. The symbol that is for some, the reverse of E actually. This meaning is for some, is read as there exists for some, for any, like. Then third point, for some X belongs to D P of X, or for some X P of X. Next, the variable appearing in for all X P of X or for some X P of X, the whole variable called a bound variable. For all X P of X is bound variable. Next, negation of predicates. That's De Morgan's laws. Negation of for all X comma P of X, that is equivalent to for some X negation of P of X. This is De Morgan's law for predicates. Negation of for all X comma P of X means it is equivalent to for some X negation P of X. See the example. If P of X is a statement X has won a race. X has won a race. This is a statement P of X where domain of discourse is all runners, then the universal quantification of P of X is for all X P of X. In this actually real meaning, every runner has won a race. Every runner has won a race. This is universal quantifiers. Applying negation of this statement, it is not the case that every runner has won a race. It is not the case that every runner has won a race. What is the actual meaning? Some runner won a race. That is, some runner won a race. Therefore, its negation is there exists at least one runner who has not won a race. So, therefore, for some X is not P of X. Hence, negation for some X P of X is equivalent to for all X negation P of X. Hence the slide. Thank you.